Problem 3 is our electric potential integral problem. In this problem you've got an arc of charge which forms a 90-degree angle of a circle. So in part 1 we want to divide the charge distribution into little elements. So let's draw a little space here and call it dq. And I'm going to choose the angle theta here to represent its position. So we know in this case that the integral of dq will give me the total charge. And we also know that the integral of d theta here should give me pi halves. I'll go ahead and write my little d theta right here too. Okay, part B. Express the element's charge dq in terms of the variable and or the infinitesimal size. So in this case, the charge is going to equal the charge per unit length, lambda, which is given. Let's go back up here and show that right here. It gives the charge per unit length in the statement of the problem. So that will just be lambda times the length of the little piece of arc. So this little piece of arc right here has a length ds. But we know from geometry that the length of a small piece of arc is equal to the radius of the circle times the angle d theta in radians. So this is the answer to this problem. I've got the amount dq in terms of the variable d theta. Now we can check its consistency with what we've written here by evaluating this integral explicitly. So dq is then the integral of lambda r d theta. Lambda and r are constants, so we have integral of d theta. Now what's that? We'll go back up here. D theta is pi halves. So this gives us lambda r, let's put the pi in front, over 2. That's the answer. Now, what the heck is that? Is it right? Well, let's see here. This, if you think about it, if this were a complete circle, then the total charge in that case, I can write that out here, would be lambda times 2 pi r, right? Because 2 pi r is the circumference of a circle. So if it were an entire circle, it would be lambda times 2 pi r. However, this is a quarter of a circle, so we have to divide that by 4. And sure enough, that is an equality, because when you divide that, you get lambda pi r over 2. So this checks out. Part C. Well, this is pretty easy. Let's look back at the diagram here. The position vector r is of the point P relative to the charge element. So that's actually this vector here. And as I integrate from theta equals 0 to theta equals pi halves, this vector will change. It will point in this direction, and then when it gets to the bottom, it will be pointing up. But its magnitude is always equal to capital R, isn't it? So that's pretty easy. Part D, the expression for the contribution from each charge element to the electric potential is K times the small amount of charge over the distance R. Now plugging in from what we had before, we had dq is lambda r d theta. That's a previous result that we had. And little r is big R. Those r's cancel out. I love it when that happens. You get k lambda d theta. This may look a little strange because it doesn't depend on, it's a constant, right? But if you think about it, each charge element, because it's a circle, is the same distance from the center. So each little piece of charge contributes the same amount to the potential, so it shouldn't really depend on the angle theta. Alright. Last part. We add all this stuff up. to get the total potential. So we just write an integral sign in front of all that, and that's pretty easy. And this equals k lambda, because those are constant, times d theta, which equals pi k lambda over 2. All right, let's just check and think if this makes sense. If you remember, the charge distribution is a quarter circle, and here's the point here. And all these points are the same distance r from the point in the center, right? So the potential, if you think about it, if you were to guess, you would guess that the potential would be the total amount of charge divided by the distance of all the charge from the point in question. Since all the charge is at the same distance, you just get this over r. So using what we derived before for the total charge, remember it's lambda times a quarter circle. A quarter circle, well, let me just rederive it here. It's the circumference of a complete circle will be 2 pi over r. A quarter circle is divided by a quarter, and you divide that by r. The r's cancel. A 2 cancels with the 4 to leave a 2 there, and we get k lambda pi over 2, which is in fact exactly what we got using the method. Okay, this problem is a little tricky. The calculations don't turn out not to be very difficult. However, the reasoning, can be conceptually a little tricky. First, let's look at the part A here, asking which side of the capacitor must be held at a higher potential in order to reject negatively charged proteins. Well, let me kind of work backwards from the force. If we want to reject a protein, remember it's going to enter from the left. So the particle is going to be flying through here. We want a charge back directed towards the left. So we want the force to be pointing left. Now, we're trying to reject negative charged proteins. So if you remember the relationship between the electric force and the electric field, it is equal to the charge times the electric field. So the charge on a negative protein would be negative. Therefore, the force is in the opposite direction of the electric field. So we want the electric field pointing to the right. So we got that. Now then, the potential. We must remember that the electric field, and this comes from this relationship, that the change in potential is minus E dotted into delta R. This relationship implies that the electric field points in the direction of decreasing potential. That implies that the potential of the plate on the left will be higher than the potential of the plate on the right. So the answer here is the right. So the answer here is the left side. Another way to see that this has to be true is just think about a negative particle in here. Once it gets in here, which side is it going to be attracted to? If you think about it, positive charges have higher potential near them than negative charges in general. So you want the particle, once it moves in here, to be attracted back to the left, which implies that this side must be at a higher potential, because negative particles are attracted to positive particles. Okay. Next problem. What minimum magnitude of potential difference is needed in order to reject a protein with a negative charge of negative 5e if it enters with a kinetic energy of 15 keV? Now, in the case of the minimum magnitude of potential difference, you can imagine that if you're increasing the potential difference between these two plates, you're going to increase the magnitude of the electric field, and there's going to be a larger and larger effect. But in the case where it's just able to reject a protein, that protein would enter here and it would slow down and just come to a stop as it reaches the other side. And if you were slightly higher potential difference, it would come to a stop just before it reaches that and go back. So we can apply conservation of energy to solve this problem. In the case where it enters with 15 keV of kinetic energy and reaches the opposite side with 0 kinetic energy, that's the situation we want to analyze. Okay, to make this clear, let me just draw, some initial and final diagrams. So initially, we have a particle on this side. It's moving to the right with initial velocity v, and in the final situation, it hits the right side right here, and its final velocity is, in fact, 0. Okay, and we know its initial kinetic energy is 15 keV. And we know its charge is minus 5e. So in this case, we're going to use the conservation of energy to solve this problem. So the conservation of energy says that the total change in energy should be 0. And in the case of an electric potential energy, you have the charge times the change in potential plus the change in kinetic. All right, now then, the charge is minus 5e. Delta V, of course, is the target variable we're trying to solve for, and the change in kinetic will be the final minus the initial. Now I realize as I wrote this that I wrote the initial, but I didn't write the final up here, but the final, of course, comes from the initial here. The final velocity. Of course, the final kinetic energy is 0. Okay. So let's carry on. We have 0 equals minus 5e delta v minus k0. We can solve this for delta v. If we think about it, the only unknown here is delta v. So we can solve directly for delta v, and we get minus k0 over 5e, which is minus 15 keV over 5e. And as we talked about before, we know that the e's cancel here. So we get minus 3 kilovolts. All right, now you'll notice that we get a negative sign here, and let's just check to make sure that makes sense. That's the change in potential when we go from the left side to the right side. Let me go back and look at this diagram. So when you go from the left side to the right side, that's a change in potential. But remember, the left side is at a lower potential, so the change should be negative. So the negative makes sense. All right, in part C, we're also going to apply conservation of energy. So let me draw an initial and final diagram here. There's the initial, and there's the final. In the initial situation, we have a particle entering from the left, moving with an initial velocity v0. Now I'm also going to consider the limiting case here. Again, let's think about this. Remember, the electric field is pointing from left to right inside there, right? So that means the force on the particle, of course, moves back to the left. Now that force is proportional to the charge. In the statement of this problem, the polarity is fixed, and since the distance between the two sides is fixed, although I don't give you what that distance is, but it's fixed, the electric field is fixed. So the force only varies as you change the charge. And you can imagine that as you increase the charge, the force acting backwards, slowing it down and eventually perhaps turning it around, sending it back to the left, will increase as we increase the charge. So there's a critical charge value at which the charge comes in and just stops on the right side. And if it were to continue, it would fall back out. So any charge less than that is going to actually make it through, and any charge greater than that, with a magnitude greater than that, will stop before and be kicked out. So we're going to try to solve for that limiting case. Let me just summarize some of the things we know here. We know that the delta V here is going from left to right is minus 3 kV. That's assuming the polarity that we determined from part A. We know that the initial kinetic energy of the particles is 10 keV. And we also know the charge on the particle, in this case, is going to be N times E. Okay, so let's begin solving this problem. First, we're going to apply conservation of energy. The total change in energy should be 0, and that is going to be the sum of the change in potential energy will be the charge of the particle times its change in V plus the change in kinetic. Okay, let's go ahead and simplify this. Now the charge is going to be N times E. Now N here, if I didn't explain, N is some integer. Make sure I get that clear. N is an integer. So that's like minus 3, minus 2, minus 1, 0, 1, 2, etc. So I've got the charge indicated here, that's Q, is N some integer times the fundamental charge unit E. E is a positive number. Then times delta V. Delta V we know. And then the change in kinetic, of course, is final minus initial. Now the final is 0 because we're considering the limiting case where it just comes to rest. So it goes to 0. Alright, so let's continue on with this equation. What we want to solve for now, because we're wondering, let's think about what we know. We know E, we know delta V, and we know this. The only thing we don't know here is N. Is that the target variable? Well, if you think about it, it's asking if here which proteins get through and which pass through, right? Which charge states get rejected and which get accepted. So that is what we want to find out. We want to find out the critical N that will stop, and then N larger or greater than that will either get through or not, depending on its sign. That will become clear as we solve. So let's solve now for N. We can take the minus K over to the other side. I write this on this side. And we divide by E times delta V. And what do we get? Let me check my numbers here. K naught, I'll have to go back here. K naught, that's 10 keV. So K naught is 10 keV. We divide by an E times 3 kV. We can check that. Is V, I got to go back up here because I have a short memory. Let's see. Delta V is minus 3 kV. Ooh, minus 3. Let's put minus 3 kV in there. Minus 3 kV. So that's a minus sign there. Okay. Notice the E's, of course, cancel. K's cancel too. The V's cancel. And all we're left with is a pure number without any units, 3.33. Now what does that number mean? If the charge was minus 3.33 times e, then that particle would come exactly to a stop. However, if the charge magnitude is greater than that, then the force will be large enough to bring it to a stop before it reaches the end. That implies that for n less than minus 3, because n equals 3.3 is impossible. It has to be n equals minus 3 or n equals minus 4, etc., etc. These will all get stopped. So the rejected proteins will have will be the ones with n is minus 4, minus 5, minus 6, etc. And the accepted ones will be n equals minus 3, minus 2, minus 1, 0, 1, etc. I'll just summarize that answer then if it doesn't quite make sense. The total charge on the particle is n times e, and we must have n less than or equal to minus 4 to be rejected, and n must be greater or equal to minus 3 to be accepted.